morning. Say hi, Kima. Good morning. Hi. Hi. Okay, let me get my iPad set up and we'll get started. Okie dokie. There we go. Okay. All right, look, we got 12 people already. That was fast. That's fantastic. Okay, here we go. You guys can't see that, eh? Let's see here. What's going on? Video capture device. Uh-oh. Hold on 1 second. Sorry, I thought I could start the stream without my iPad first. I was just kind of, okay, so I'm gonna disappear for a second, but I'll be right back. I think the stream should continue to work though, so hold tight. Yeah, so I'm back, as you can see, but my streaming thing doesn't want to work right now. Not really sure what's going on. Let's see here. Okay, unplug that. Plug it in again. Come on. Unplug this. Unplug that. Oh, come on. Is that it? Sorry about this, guys. Okay, I don't really know what's going on here. Unplugging things, plugging them back in. Okay, you know what? I'm gonna quickly reboot. So I will be back in 2 minutes. The stream is gonna keep going though. It's just gonna be like a black screen. So hold tight. Sorry about this. Okay, I'm back, and it looks like it's all working now. Just needed to reboot. Not sure what went wrong there, but whatever. We're if you can hear me, and it's all good. What to open widget? Uh-oh, YouTube is not written out. Let's see here. What's this all about? Okay, looks like things are going okay. Can you guys let me know if this is working? I have the impression that it's finally working now. Can't hear anything? Really? My microphone seems to be working. Okay, so it looks like people can hear me. It looks like it's just yeah, maybe you've got the volume turned down or something. Okay. Great. So we're not gonna do too much like theory today. We did a lot of theory yesterday, learning about the different types of number systems, like the natural numbers and the integers, the rational numbers, the real numbers. We talked a little bit about irrational numbers. So what I thought we could do today is just sort of do kind of like an interactive thing. So yeah, it looks like things are going okay. Okay, so I'm gonna try to make this a little more interactive. So what I'm gonna do is I'm gonna list a few numbers, and I'm gonna give you 2 minutes to sort through them and determine which number systems each of the numbers belong to. So, oh, by the way, I did put a little note on the website about number systems. So if you want, you can take a look at it. I'd recommend you read it. It's very short. It's just it's about 1 page, and it talks about each of the number systems, and there's a few extra notes on it. I think it's a good read. It seems to be fairly concise and kind of summarizes everything that we talked about yesterday. And it also has the Math BB computer font, so you can take a look at what those symbols actually look like in terms of their font face. So yeah, we're going to do some examples now. Okay, so yeah, I'm gonna tell you a set of numbers, and I'm gonna ask you to set them up into each set. So so my question is, which number systems does each number belong to? Okay, so the set of numbers that I'm gonna have is well, I'm gonna have -2, I'm gonna have 0, I'm gonna have 4, I'm gonna have 1 2/3, 1 2/3. I'm gonna have the square root of 2, and I'm going to have pi. Okay, and the number systems that we're going to be talking about are the natural numbers. Let me make that look a little bit nicer. I'm going to zoom in a bit. Okay, so I've got the natural numbers. I've got z. I've got the integers. I have the rational numbers, q, and we'll do the irrational numbers, p. But remember, this isn't actually a number system. It's just a set of numbers. It's not a number system because it's not closed under addition and multiplication. So we have the rational numbers, the irrational numbers, and then I've got the real numbers here. Okay, so tell me, which number systems do each of these belong to? So, you know, maybe what we could do is we could even make a little grid here. I'll sort of do this like that. That looks good. And I'm going to do check marks. So, like, let's say, okay, I'll give you a hint. 4 is a natural number. So I will give a little check mark to number 4 over here because it's a natural number, right? Like if you follow this row and this column, right, they intersect right there. So I'm going to give myself a check mark there. So can you put one number into multiple categories? Absolutely. You definitely can. So I'll give you a hint. 4 is a natural number. It's also an integer. It's also a rational number, which means that it is not irrational. So it's not in this P, but it is a real number. So 4 is in 4 different number systems, okay? So I'm going to give you 2 minutes to do this. Let me just put up a little timer here. Here's a little timer, and I hope you can still read that. I think you should be able to read that still. Here, I'll do this. I'll make it a little bit, that's better. Okay, so I'm going to give you 2 minutes to do this, and we'll go over the solution together. So 2 minutes starts now. Okay, here we go. Okay, so let's talk about these different numbers. So I'm going to start off with -2. Let's see which sets -2 is in. Well, -2 is not a natural number. Remember, a natural number they're just positive numbers, so it's not in that set. It is an integer though. It's an integer. So if it is an integer, then that means that it must be a rational number as well. And if it's a rational number, it cannot be an irrational number, right? Like these two should have nothing in common, right? So there should be nothing in common between these because they're opposite sets, right? But if it's a rational number, then it must be a real number as well. Okay, so something that you have to understand is that these sets are kind of like, they're like babushka dolls, right? Like if you're in one, then you're in the next one too. So I'm going to draw a little diagram in a second that should help illustrate this. So again, 0, depending on who you ask, could be or could not be a natural number. But in this class, we're going to assume that 0 is not a natural number. But it is an integer, and it is a rational number, and it is a real number, so that's good. Okay, so we have, well, we already did 4. 1 2/3, so that is not a natural number, it's not an integer, but it is a rational number, and it is a real number. The square root of 2, that is irrational, so that means it's none of these, but it is this one, and it's a real number. And pi is also irrational, like that, and it's also a real number. So all of these numbers are real numbers, and only a few of them were irrational. And yeah, so that's that. Oh, excuse me. So, oh my goodness, excuse me. Okay, so I think at some point, did I do this yesterday? I just want to, or not yesterday, but the day before yesterday. No, I don't think I talked about subsets, but I did. Oh yeah, I put a note of this in that little page that I put on the website yesterday. So I put up a page on our website yesterday. So if you go to the grade 9 section, it says a note on number systems. There's something on that I want to go over, and in particular, it's about how, like, if you're in this set, then it means you must be in this set, and this set as well, right? So that's what I want to talk about a little bit. Just a quick note on that. So in set theory, so that's where we think about different sets, and sets are just groups of things. So in set theory, when the contents of a set A are all contained in a set B, we say A is a subset of B, okay? And we write A is a subset of B, okay? So that's like what we have. So in this case, in our case, in our case, we have, well, the natural numbers, that is a subset of the integers, okay? And that is a subset of the rational numbers, and this is a subset of the real numbers, okay? So this is an important fact because it tells us that any natural number is also an integer, and any integer is also a rational number, and any rational number is also a real number. So we have this little diagram here that I'd like us to draw. So what I'm going to do is I'm going to draw this box, okay? So this box is going to represent real numbers, okay? So these are all the real numbers, okay? So I've got real numbers over here, real numbers, okay? Now, some real numbers are irrational. Okay, so I've got this sort of maybe what I'll do is I'll say yeah, so here's my set of real numbers. Some of them are rational and some of them are irrational. So what I'm going to do is I'm going to sort of split this up, and these ones over here, these are going to be the irrational. So some of them are irrational and then some of them are rational. Okay? So in my set of real numbers, I've got rational numbers and irrational numbers. And in this little group of rational numbers, some of these numbers are integers. Right? Okay, so some of these rational numbers are integers, and even within that set of integers, we have that some of these are natural numbers. Okay? So all of these are real numbers. Everything in this box is a real number. So the way you can sort of think about it is that you can be like, okay, well, let's say I've got a integer right in here. So there's my integer. This integer is a rational number, which means that it's a real number, but it's outside of this box of natural numbers. So, I mean, depending on where you put your dot, like this dot here, so maybe we can actually try putting a number in here. So this would be like a number 7 could go here, right? Because that's a natural number, it's an integer, it's a rational number, and it's a real number. We could have like -8 over here, right? So that's an integer, but it's not a it's an integer, but it's not a natural number. But since it's an integer, it's rational and therefore real. And then 2/3 could go over here. That's a rational number, which is also therefore a real number. And then finally we have irrational numbers, which would be something like pi, right over there. Okay, so that's kind of how all the numbers work with one another. I think that was pretty much all I wanted to show you. However, there's one more set that I want to show you, and this is kind of like a bonus set. We're not really going to talk about this set pretty much at all this year, and you probably won't see this set not until, like, I don't know. I mean, it doesn't really come up in the Manitoba curriculum, and we don't really need to talk about it, but it may come up in some sort of novel situations. So the other set, like the last set of numbers, and this is like one of the biggest sets of numbers, is the complex numbers. Okay, so these are the complex numbers, and I just want to bring it up because we're talking about number systems. We're not going to be using number systems, but hey, why not? Why not learn about the complex numbers? It's a really important set in mathematics, and especially in algebra. It really solves a lot of problems in algebra. So the complex numbers came out of algebra. They came out of a problem in algebra, and I believe it was Carl Friedrich Gauss who discovered the complex numbers. And my cat here is trying to sneak up on me and changing stuff on my iPad. Okay, Goosey, say hi to everyone. Okay, why don't you go up here? Yeah, and just stay there, okay? Yeah, that's much better. Much better. No, she really just wants to lie on top of my iPad. It's because it's hot. It's warm. It's like a little heating pad because they actually do get quite warm because it's charging right now. I can't. My battery isn't big enough to last all day, so I just leave it on the charger, and therefore it's charging the battery, and then the processor in here gets really warm, so she really likes that. She likes to lie right on top of my iPad, especially when I'm working. Yes. Okay, so the complex numbers. What are the complex numbers? So with the complex numbers, again, it's like it's outside of this set. So this would be the complex numbers here. So the complex number. So any of these numbers can also be considered a complex number. And a complex number has, so the main thing that sets it apart is this number I. and I is equal to the square root of -1. Okay, so once you include this value, because you may have noticed, like on a calculator, you may have tried to do the square root of -1, and it might give you some kind of error. So the complex numbers are just numbers that are like, okay, well, you know what? Let's just allow ourselves to take the square root of -1, and let's assign it a value. Let's say that whatever it is just equal to I, right? Kind of like how at some point we didn't believe that a number could be negative. It took us a very long time in the history of mathematics to accept the fact that a number could be negative. And it is a very abstract idea. I mean, how can you have because numbers are supposed to represent values, so how could you have like a negative cup of coffee? Like it's a hard thing to wrap your mind around when you really think about it. So just in the same way that we had a hard time, accepting the fact that numbers could be negative, there were actually people who literally were murdered and were martyrs for the fact that a number could be irrational, and we've seen irrational numbers, like the square root of 2 is irrational, the pi is irrational. People used to think that a number couldn't be irrational. So all these things I'm telling you that this exists, and you kind of accept it, but it took a long time for humans to discover these things, right? This isn't something that, like the person who discovered that there were irrational numbers out there, nobody told them, right? They had to discover that for themselves, and that's quite the accomplishment. So you can imagine that a complex number is kind of in the same vein that you might say, okay, well, that doesn't work. You just can't take the square root of a negative number. I've known that my whole life. Well, turns out you can. And all you have to do is just say, okay, let's just do it, and let's assign it a value of I. And it turns out when you do that, then everything just works, and everything is fine. And yeah, you're absolutely right. It was math cults in ancient Greece who killed, I think it was Hippocrates. Yeah, I'm pretty sure it was Hippocrates who presented to our favorite Greek mathematician Pythagoras. He said, and they were on a ship together. Here's a little piece of mathematical history for you. So Hypatius, it was Hypatius. Let me do a quick Google search for Hypatius. I think it was Hypatius. And I don't know if you can see this, but my cat is licking my coffee. Was it Hypatius? I think it was Hypatius. Maybe it's Hippocrates. Hippocrates, square root of 2. Who was it? Maybe it was Hypatius. You know what? I forget his name. I'm sorry. It's some old Greek dude. He discovered, and they were on a ship. I think they were sailing across the Mediterranean Sea, and they were on a ship with all the Pythagoreans, because Pythagoras, that guy with a squared plus b squared equals c squared. First of all, he didn't invent that. He didn't discover that. That was known for a very long time. So that was known in India for several hundred years before this. So he was not the first, and he did not discover it, but he popularized that idea. That's a very important point, because we associate the Pythagorean theorem obviously with Pythagoras, even though he had very little to do with it. He just popularized it. Anyway, so he was on a ship. I think it was Hypatius, some old Greek dude who knew his stuff. And one of the big things about the Pythagoreans is that they were a cult, and that it was there was a religious aspect to their mathematics, and they believed, like in a very spiritual way, that all things in the universe could be described as a ratio. And they were right about a lot of things, and they discovered a lot of major things about music and how scales work with proportions. So when you kind of take a guitar string or something, and then you cut it in half, that's like 1 octave higher. So they looked at all sorts of things with proportions, and they thought that everything could be written as a ratio. In other words, they thought all numbers were rational. And then this guy said, hey, well, you know what? You got this whole a squared plus b squared equals c squared thing, right? He said, okay, so you've got a squared plus b squared equals c squared. But what if these are both length 1? And then what's this length? Well, this would be the square root of 2, and he gave a proof that the square root of 2 is irrational, that you couldn't write it as a ratio, and it's actually not that hard of a proof. You can look it up on the internet. I think Khan Academy has an excellent video on why the square root of 2 is irrational. Anyway, he presented this proof to Pythagoras while they're on their boat sailing across the Mediterranean Sea, and Pythagoras said, that's preposterous. That contradicts everything about our religion and how everything is supposed to be rational, and that's enough. You need to die. And he threw him off this ship and killed him, all because he gave a mathematical proof. And then it wasn't much longer before Pythagoras realized that this guy was correct, and then they changed their whole religion to accept the fact that numbers could be irrational. So yeah, irrational numbers were like that. And I see in the chat we've got what about 1 over 0? Does that have a number set? Not really. It's not so much 1 over 0, but there are some number sets that include infinity and negative infinity. In fact, I believe, if I recall correctly, now it's been a while. It's been a long time since I've worked on this, but I believe that positive infinity and negative infinity are actually complex numbers, because we always say, oh yeah, infinity is not a number. It's not a real number. If I recall correctly, I believe negative infinity and positive infinity are complex numbers, because there's a way of thinking about complex numbers as a sphere. You can kind of think of them as a sphere, and kind of like how we think of real numbers as like a number line, right? We think of real numbers as a number line, and if you in a lot of ways, complex numbers can be thought of as a sphere, and I think positive infinity is like the North Pole, and negative infinity is the South Pole. But let me just double check. I don't want to give you false information here. So complex numbers infinity. Yeah, maybe not. Yeah, you know what? It's neither here nor there. I don't think we need to really worry about it. So yeah. Yeah, you know what? It is a complex number. So yeah, I wasn't making this up. You can look it up. So this in like sort of university level mathematics, if you ever want to take it, this is from a course called Complex Analysis, and it's where you analyze complex numbers. So this is a way of thinking about complex numbers. It's called a Riemann sphere, and it's kind of like how, yeah, like I was saying, you can have like a real number line, you know, and it's like a model for your numbers. So like obviously like the real numbers aren't just like a line, but a number line is a great way to model real numbers, right? Because you have all these cool things like, oh yeah, if your number is like over here and it's further to the right than your other number, then the bigger number is on the right. And there's all sorts of cool things that you can do when you have a nice model. And in the same way, you can have a Riemann sphere to represent your complex numbers, and then the north and south pole of your complex numbers represent positive infinity and negative infinity. But as for 1 divided by 0, which is a question in the chat, 1 divided by 0, it has to be undefined. So this is undefined. Defined. So one thing you have to understand is that anytime you define something in math, if you want to have something that is well defined, then you have to make sure that it's consistent with everything else that you know is true. That's basically the main theme of like abstract mathematics and algebra, is that it has to be consistent. So we know that multiplication and division are inverses of one another, that they undo each other. So what that means is that, let's say that we had that 1 divided by 0 was something. Who knows what it is? Let's call it x, okay? Doesn't matter what x is. Let's just see what happens when, if we were to allow 1 divided by 0 to be equal to something, right? Let's say that it's equal to x. Who knows what it is? Who knows which number system this even belongs to? Like maybe let's invent our own number system that accommodates this one thing. But the thing is that because 1 and 0 are in our number system, it means that our number system is going to be like bigger than all of these, which means that it has to be consistent with everything that we know about 1 and 0 and multiplication and division. So if 1 divided by 0 is equal to x, that means that 1 is equal to 0 times x, right? Because multiplication and division are inverses of one another, right? So, well, and the thing is no matter what number system you're dealing with, like you could be in the natural, well, I guess not the natural numbers because we're not dealing with 0 right now, but like any, like the integers, the rational numbers, the real numbers, doesn't matter what number system, even the complex numbers, 0 multiplied by anything is 0. So all of a sudden now you've got that 1 is equal to 0. That's a contradiction. So that's why 1 over 0, you won't find a number system that has that. So, oh yeah, it can be written as blah, 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 blah. Yeah, okay, so yeah, I really like what's in the chat here. So yeah, so infinity is not a number. It's just given to a very large number that cannot be numerically represented. Yeah, absolutely. So yeah, it's not a value. Going back over here, infinity is not a value. It's like, and I've mentioned this before, it's kind of like a direction, right? Like north and south. So yeah, on the complex plane, you can think of positive infinity and negative infinity as a north and south pole of your complex plane, written as a Riemann sphere. So these are great conversations. I'm really happy that we're talking about these things. So yeah, as for complex numbers, a complex number is not just multiples of I. A complex number has the form a plus b times I, and the a, this would be the real part, and this we would call the imaginary part. So so it's a sum of two parts. So that's what complex numbers look like. Anyways, this was a lot of fun to talk about. I really enjoyed that. Let's see. I think that was pretty much it that I wanted to talk about for today. Yeah, I'm gonna post some homework. I don't want to go crazy, but I've got this nice worksheet here that I'll turn into a PDF and I'll post on the website. So, how come on the calculator square root of -1 is an error? It's because calculators aren't set up to handle complex numbers. So I believe that, like, if you have a graphing calculator, I wonder if this graphing calculator can do it. Let's try it. Square root of -1. Yeah, okay, so here we go. So on my graphing calculator here, I don't know if you can see that very well. So I did square, it's kind of giving some glare, eh? Anyways, it says the square root of -1 gives me an error, but it gives me, but if I actually hit it, you'll notice it says error, non-real answer. Non-real answer, which means that this is not a real number. So it's saying that, yeah, okay, it's not an answer, but at least it's saying that it's non-real, right? So yeah. Oh yeah, so do we have an exit slip? Yeah, so the exit slip for today is... Let's see here. Yeah, domain error. Yeah, absolutely. Domain error makes a lot of sense because the domain of, like, domain kind of means like the area that you have to like roam in, right? Like you might have heard of like you can imagine like an old king being like, oh, this land is my domain, right? Like domain kind of means like the area that you have to play around in. So your calculator's domain is the real numbers. So if you say you invented Pythagoras theory, then can we call it Aaron theory? You would have to convince people. I'm not convinced. I mean, that's the whole thing about these communicators of mathematics, is that they have to convince people that things are true. Okay, what I'm going to do is... Okay, I'm trying to find a good question here for the exit slip. Okay, the exit slip for today is... so exit slip for today is name all number systems that 3.3 repeating belongs to. Okay, so there's your exit slip for the day. Okay, looks like you have a following now. So just be careful. I don't think that these sort of mathematical cults have a very good track record. I think that you may be at risk of a cult forming. So be careful with your cult. Anyways, yeah. So the exit slip for today is to name all number systems that 3.3 repeating belong to. Okay, so we didn't really talk about repeating decimals today, but we did on Wednesday. So you might want to sort of go back to Wednesday's notes. Yeah, so there's your exit slip for the day. I'm gonna sign out. You guys have a good weekend. I'll talk to you guys on Tuesday of next week, right? So we're meeting every second day, so that would give us till Tuesday. Oh, you want to throw them off the boat? Uh-oh. See, this is what I'm talking about. It's no good having a cult. These cults are dangerous business because you don't know much of complex. Are repeating decimals complex? Yes, they are. But there are other things too. Okay? Yeah. So yeah, just to be clear, like right over here, like all of these numbers are a subset of the complex numbers, right? So all of the numbers that we've looked at so far are not only are they real numbers, but they're also complex numbers. And complex numbers also include things such as the square root of negative values. So do we write complex as well? If you want, yeah, you could write complex if you want. I won't consider it wrong if you don't write complex numbers, because complex numbers is not really in our domain of our curriculum. So that's not really what we're talking about. Okay, so yeah, I'm gonna sign out. Stay tuned for some homework. I'm just gonna post a little worksheet on there. It's kind of a long worksheet, so I'm not gonna get you to do the whole thing. I'll kind of do like a every second question kind of thing. Anyway, have a good weekend, and I will talk to you guys on Tuesday. Okay, bye-bye.